supposed to show that the complex numbers of the form a plus bi with a and b rational numbers satisfies the axioms of the field under the normal addition and multiplication. So when I first read this, I was a little confused. I was just ready to run down the checklist. Complex numbers, I know they're a field, and I can just say they're closed, and I was about to run through all the normal properties and just kind of write them out and just prove it that way. And but I was missing this part here, that rational bit, because we're used to complex numbers are defined as in the form a plus bi with a and b real numbers. And so this is a special subset of the complex numbers such that a and b are forced to be rational. So a smaller subset of complex numbers where a and b can't be anything, they can't be irrational and stuff, they're forced to be rational. So, so it provides just a few extra steps to prove some of these. So the first thing we have to prove is that they're closed under addition, and if that means, so that means that if I took any two elements in this set, a plus bi and plus c plus di, I would get a plus c for my real part and b plus di for the imaginary part. And so if this is my new number, is that still of this form, where this and this are still rational? And yeah, they're still rational, because a plus c, if you add in two rational numbers, you get a rational number. And same thing here. So these numbers are still rational. So it's kind of using the idea that rational numbers are a field, knowing all the properties work for that, to prove that all the properties work for this construct, this a plus bi. Yeah, a little annoying, but we'll do it. Associativity, when you look at the sample answer, they actually just kind of assumed associative. The fact that these are rational numbers don't mess with it. They kind of sidestep it. They say, oh, we already know complex numbers with real numbers are a field, so therefore complex numbers with complex numbers with real numbers are a field, they'll satisfy the associative property, and rational numbers won't change that, nor will they change commutativity. Same with the ones for multiplicative there. So the fact that these numbers are rational and not real really don't affect those properties, and the sample answer just kind of assumes that. Now, if you're scared of it, and I was, when I first read it, I'm like, I didn't know that we were allowed to assume it and prove this, right? So you could just write out a quick, basically definition of associativity and kind of work through there. And they mentioned that the idea that they're rational doesn't change it. Yay, annoying stuff. But okay, so the identity property, this could, the fact, we know that complex numbers have an identity of 0 plus 0i. And so now your only check is to make sure that these numbers here, they were real. Are they still rational? Well, yeah, 0 is a rational number, so this is the identity element, and it's still contained within this set. So check. How about inverse? We know that the inverse is normally negative a minus bi, and again, you're just wondering, are a and b still rational? Well, yes, it is. Distributive is another one that they assumed because they already knew complex numbers with real coefficients worked for distributive. So you could just write it out real quick if you wanted. When we get to the second guy, we have to show that they're closed under multiplication. So if you took any two complex numbers like this and multiply them together, I should make this c plus di, sorry. A plus bi times c plus di, I'll get ac plus adi plus bci plus bdi squared, and that's just minus bd because I squared is -1, so this is